So today I want to tell you how to turn an ordinary kind of mediocre battery eliminator, or sometimes power supply with fixed voltages. Probably this should have been 3, 4.5, 6, maybe have a 5 and 6, 9, 12, something like that. It would be more useful, but this is a bit old, and we used to have 2-volt batteries, lead acid 2-volt batteries for 2 of them, 6 for 1.5-volt batteries in series, 8 for 4 lead acid batteries, 10 for 5, and 12 for 6. It's basically that. This would be for lead acid batteries. Problem with this is that it is kind of mediocre compared to today's standards. So let's get a cheap multimeter. It's actually accurate, no problem with that. And look at this, what's going on here. So as you can see, it's out of scale. So this is the 12-volt setting, and it's 22.5. 20 at 10 volts, 15.5 at 8 volts. Okay, nothing here. No, 11.8, 11.9, almost 12 at 6 volts, 8.3 at 4 volts, more than double, 4.7 at 2 volts, yeah, more than double, same thing. The problem here is that this is not regulated. And because it is not regulated, it depends a bit on the input voltage. So if, for example, originally the transformer was made for 220 volts, and today we have 240, this is one of the things that happens. The other thing is that because it's not regulated, you have the peak voltage coming out of here. In this case, it's way more than peak voltage. The peak voltage would be nominal voltage times the square root of 2, so it's way ahead, way over. So let's open this and see how we can improve it. Actually, this is a very common thing in any unregulated power supply. So probably if you got some power supply or transformer with different voltage settings that is not an SMP switch mode power supply, it's probably going to overshoot, because if it's not regulated, it is going to be over the nominal voltage. Just even if it's well designed, and you will always have peak output voltage here, and when it's at full load, you get the RMS, which is probably going to bring it down closer to the nominal voltage, but it's always over in my experience. We can actually improve this, and what we are about to do here applies to any of those transformers, unregulated transformers or power supply, or even if you want to design your own power supply, in this case battery eliminator. This one is made in India. It's in quite good condition for a 40-year-old thing, but the same thing will apply to anyone, any power supply that is unregulated, and probably to all that you get from China. You will have the same problem. So let's do it. Let's open the thing. Power it off first, because it's connected to mains, so better be safe than sorry. And here is the thing. As you can see, no PCB, just a transformer with multiple outputs. Full wave bridge made with discrete diodes, apparently 3 amp diodes. The switch is cutting the mains power to the transformer. There's an LED connected directly to the mains power, or not after the switch, so it will turn off when the switch is off. So it's in parallel with the transformer coil. Yeah, the red wires are the transformer, and these are the mains. And 100K resistor in series, so that will give it about 2.2 milliamps over on the LED. 2.2 milliamps times 220, yeah, it's probably 44 milliwatts. Okay, doesn't overheat, so that's fine. Now we have a 25 volt 470 microfarad capacitor in series with bleed resistor 1K, so that it discharges to discharge the capacitor when the power is off. And we have a switch. I don't know why they cut this thing. Weird. So this is just selecting one of the kind of sections of the auto transformer. Actually, this is an auto transformer, not an auto transformer. I can't say that, but the secondary is made. Yeah, the secondary is made of multiple coils. And apparently they seem to be sectioned because there are 2 wires for each coming from the transformer. And this thing is selecting that. So, and because this is a dual section switch, which actually they removed one of the pins here, we can actually see if we get this missing pin here, which would select one of these. And at the same time as this pin here is going to be connecting to one of those where the coil is. If we have this missing pin here, we can use this to actually select voltages with an LM 317 or something like that. Maybe not, because this is 2 amp and the LM 317 is not going to do 2 amps, but we can select different voltages on the regulating circuit. And why not just get rid of all these coils and just get the 12 volt one and regulate from there? Well, there is a problem with that. If, for example, we want to get 2 volts and we are regulating from 12 volts, there's a 10 volt drop in the regulator. At 2 amps is 20 watts that are going to be dissipated. We don't like that. Actually, it's going to be way more, because if we actually use the, as we've seen here, it's more than the peak voltage. So we would be regulating from 22 volts, I guess that's what we were getting on the 12 volt setting. So that means that we would be dissipating 40 watts. From 22, we would be dropping 20 volts at 2 amps. We would be dissipating 40 watts on the regulator, which is bad. So what we will do is we'll keep selecting this input coils here and get, I guess it was 4.6 on the 2 volt setting, get 4.6 here, and make this the input of the regulator, and the output would be connected to the terminals. So then we would just be, even at 2 amps, we would just be dropping about 5 watts. dissipating about 5 watts on the regulator. And here at 4 volts, I guess that was 8.6 volts. That means that we would be dissipating 4 minus 8.6, 4.6 times 2, 8 something watts, and so on. It's way less than 40 watts, right? So that's what we would do. What we will do. I'm actually going to change these voltages to some more useful ones. So I'll just use a simple permanent marker to change that later after scraping it or something, or maybe I'll just use some stickers, but probably this is going to look better. So let's go ahead to that. Let's go ahead and design this on paper and then see if it works. The input doesn't look like a coil, it looks like a jammed wire somewhere. Okay, let's do it looking better, a bit better. Not much better, but it's okay. Okay, so so this is our transformer and mains input here, a switch, 100K and an LED. It doesn't matter the polarity of the LED, it's AC getting in. And here we have 2 volts secondary sections in the output. So this will in turn feed into the rotary switch. Just let's put the common terminals here, C1, C2. Now for each common we have 6 connections. 1, 2, 3, 4, 5, 6. So this would be A1, 2, 3, 4, 5. Oops, what happened? 1, 2, 3, 4, 5, 6. better do it AB. So here is the A and B, B1, B2, B3, B4, B5, B6. So this is going to be our regulator. And now here on the A, let's have 1, 2, oh, wrong. It's the other way around. 1, 2, 3, 4, 5, and 6. And now we are going to connect these things. So 2 volts, 2, 4, 5, oh sorry, 6, that was easy, 8, 10, and 12. Okay, and this A is going to feed into the bridge rectifier. So let's do that. A bridge rectifier here with discrete diodes, and another diode here. This is the negative, and again another diode, and another diode. This is the positive, and the capacitor, also connected to ground here. Okay, and now here we are going to have 0, and here we're going to have A. Okay, so this is our circuit. This is what we have in the box. But now we want to use B, which actually it's missing, is missing the terminal, but we want to use B to select voltage into the voltage regulator, and this is plus. But I forgot that at the moment we have the output terminals, like let's draw something like that, whatever. This is connected to plus, and this one is connected to ground. Okay, this is what we have at the moment, but now we are going to disconnect this thing, and let's I'll just do an example with the LM317. Although it's not going to do 2 amps, it's going to shut down at 1.5 amps, for example, for the CT version. But there are other similar regulators that can do up to 5 amps. Let's not use that at the moment. Just I don't remember the part number for that. So let's just imagine that this is an LM317. Kind of, yeah, my drawing skills. Okay, LM317, and well, forgot the pin out. Let's say this is in, this is common, and this is out. It's not like that. Maybe I should delete that thing. Just make a black box. No matter what is in here, you'll just use the right pinout for the package that you have. So here we're going to connect this thing to plus. We're going to disconnect it from there, and we're going to call this VO. Okay, let's put this VO. Okay, and here is the track. So we have a resistor here and another one here, and a capacitor, output capacitor, and an input capacitor. We already have one, but we're gonna just put a small output capacitor here, just to stabilize, because there will be a wire going from this to that, so we'll keep this one here, or probably make it a bit bigger, like make it 10 micro, okay, and this probably 100 micro, and the bleed resistor that I forgot to put here, so let's put a 1K. I forgot the bleed resistor there as well. 1K. Okay. So, what sets the voltage in this type of regulator is the ratio between these two resistors. For the LM317, the voltage on this pin will always be 1.2 volts. 1.2 volts. But the drop on this resistor will change, and it will actually be 1.2 volts lower than Vout. If we ground this pin, because the LM317 will try to keep 1.2 volts here, I mean the difference between this point and the output will be 1.2 volts. Let's actually write that with the arrows. Okay, because the voltage differential is going to be 1.2 volts, that means that if we ground this pin, we'll have 1.2 volts here. So let's say that we want to make 2 volt output. Let's say instead of 2, 4, 6, 8, 10 and 12, let's put 3 volts. Actually, yeah, let's make 3.3. It's can work as battery eliminator and as kind of power supply. 3.3, let's say 4.5, 5, 6, 9 and 12. Yeah, 4.5. No, sorry, that's the new values. 4.5, 5, 6, 9 and 12. I guess that will work. We could go through with 3.8 as well. Yeah, 3.8, we have room for that, so 13.8, not 3.8, 13.8, because 12 volts is actually not very useful. If you want to power some Arduino or something, you'll use 9 volts. If you want to power a logic circuit, you can use 5 or 3.3. If you want to use any microcontroller, you can use 3.3, 4.5. If you want to power it with batteries directly, maybe 5. Not with batteries directly, probably. 3.3, 4.5. One of these is also going to work for lithium ion. Lithium ion batteries can go up to 4.2 volts without exploding, and when they are at their lower end, it will be around 3.2 volts. So this is quite close for a lithium ion. So this will work much better. So these are going to be our new voltages here, and to calculate the voltage drop on these two resistors, first we need to plug in the formula, and let's do that. So let's call this R1 and this R2, and let's say Vout equals 1.2, no, the datasheet says 1.25 volts, and 1 plus R2 under R1. Okay. Just R2. Yeah, again, I don't get that well. I think there should be a better formula for this thing. Okay, so I adjust here is the current, and here I adjust, and it's 100 microamps usually. Now let's calculate it for 100 microamps. I adjust, it's about 100 microamps. Okay, so with that 100 microamps, if we want 1.25 volts here, and let's say we want 1 milliamp going down the thing, so for each 1K we have 1 volt. We need to probably calculate the value of this resistor first to get to the current that will provide 1 milliamp here. So let's say if it's 1.25 volts, so 1.25 volts divided by 1.25k, it's going to be 1 milliamp, but because we have 100 microamps going here, we want the value that gives us 900 microamps for 1.25 volts. So It could be adjustable. It's probably going to be better. Bars menu. How do I clear this thing? Well, there should be a clear somewhere. Quit. Oh, there's so many things, but nothing of what I want. Just an easy clear thing. I want to clear the screen. Maybe I'm being too picky. Menu. Run and back. AC compound list. Okay. So let's 1.25 divided by 0.9. This will give the value in K because we are making 0.9 milliamps. So it's 13888 K. 125 volts at 900 microamps is going to be 1.388 K. Adding those two together, we have 1 milliamp of current here. IA equals 1 milliamp, meaning now 2K, 4K, 6K, 3.3K, 4.5K, 5K, 6K, 9K, 13.8K. Okay, so we do that by replacing R2, disconnecting R2. And connecting this terminal to B. Now, there is a problem. If we now, of course, now we need to connect resistors to all these terminals, and between all these terminals and ground, let's say when this one is selected, here the B1 is going to be selected, and the problem is that the switch is not going to be making a permanent connection. So when we flip the switch, there will be a moment where the regulator is going to, this pin is going to be floating. And because it's floating, it's going to be getting the input voltage. In the output is what we're going to have is the input voltage minus 1.2 volts, which is not what we want. But we have a solution for that. It's not the best, but it saves us from burning a lot of stuff. So the 13.8 volt resistor, 13.8K, is actually going to be connected here, and we don't need any resistor there. And the resistor that we are going to put here is going to be in parallel with the 13.8K to give us the appropriate value, which is going to make our life harder, but at least we will be sure that this Vout is never going to be over 13.8 volts. There is no other way to deal with this in this switch, with this switch here. So if we could have a different type of switch, would be probably a make before break, and that would not be a problem, because we would always, while switching, have at least we would have two resistors in parallel, which would lower Vout. That would be perfect, but it's not guaranteed that this switch is going to make before break. Actually, I think it doesn't, because this kind of switch is used in multimeters, and if we make before break, we'll burn something. So let's not count on that. If it was, for example, let's say we are selecting 2 volts, and we are now going to try to select 4.5 volts. When we rotate the switch, the 4.5 and the 3.3, sorry, I said 2 volts, but meant we are in the 3.3 volt setting, and we want to go for the 4.5 setting. For a moment, the 3.3 K resistor and the 4.5 K resistor connected to these two terminals is going to be in parallel, lowering the voltage further. So the voltage would be less than 3.3 volts. We just need to calculate these two resistors in parallel to know how much, but the voltage would not overshoot. What happens is that when we are turning the switch, for a moment, it's the B terminal is not going to be connected to the B1 terminal or the B2 terminal, so it's going to be flying for a moment. So to guarantee that it doesn't we don't get like 20 something volts in the output, at least we can guarantee that we have a maximum voltage of 13.8. We will have a resistor here that is going to be 13.8 K, which doesn't exist, so we need to make some series to get to 13.8, or maybe series in parallel. So let's call this R3. Now what we need to do is calculate a value which will give us 3.3 K when it is in parallel with 13.8. Okay, so let's do that. -13.8 minus 3.3 10.5. So for 3.3 volts, we have 13.8 in parallel with 4.3, and this is roughly 4.3. Let's 3.28 K. 3.28 K. Oh, 13.2. Yeah, 3.28 K. So what we do here is that to B1, between B1 and the ground, we have 4.3 K. Between B2 and the ground, if you notice, I'm not drawing these schematics as a complete circuit. I'm actually doing it as you usually would do in a schematic capture software. So I'm using net names. You just connect that stuff. All right, 13.8 K for R3. Maybe I should delete this thing, otherwise it's a clumsy schematic. 13.8 K. You calculate that and get some value for that. Now let's do 4.5 K. So for 4.5 K, the closest one would be probably 5.6. I'm not sure. Maybe not. Maybe something like 6.8. 6.8K. Not that. 7.5K. Maybe 10K. 5.7. 8.2K. Yeah, so for let's say what we call this one, R1, 2, 3. Okay, let's call this R4, R5. Let's call this 6.8K, which would give us 13.8 in parallel with 6.8 equals 4.555 K. So this would be a well-charged group of three 1.8 volt batteries. So now let's go to B3 and see what value of resistor we have to get 5 volts. It's not going to be probably much more than 6.8. It's going to be like, let's see, what is the next value in the series? Maybe 8K. 8K. So 13.8 in parallel with 8K, it's going to give us 5.06. Okay, so this would get us very close to 5 volts. Not a big deal there. We have a bit over 1% error, which is not a big deal. Now before that one, well, here we want to have ground. Okay, maybe I could just draw a line there. 6 volts. So for 6 volts, let's try 1.2K. 9.1K. I'm just trying values and using an online calculator for parallel resistors, and yeah, I could just come up with a formula that would give me what I need to get the right value right away, but well, that didn't work. It would take me a long time to do that, so I can just try to plug in standard values. So apparently what works is about 10.5K, maybe 10.6K. Yeah, so 10.6K for, this is R6, this is R7, 10.6K. Let's separate this 13.8 in parallel with 10.6K equals 6. Yeah, 6K. Now, next value, it's going to be B5. Okay, and for B5 we want to have 9 volts, and so let's say 20K, 33K, it's too much, so 27K, yeah, 27K is alright. So 13.8 in parallel with 27 equals 9.1K. So we will have 9.1 volts, not a problem at all. So these are our values, so 27K. And that's how we do it. Let's see how much power we are saving for each here. Instead of regulating from 2 volts, originally the voltage here was 22.5 volts, and to regulate down to 2 volts we are going to have let's say 2 amps here. Let's imagine that we are consuming 2 amps at 2 volts. We are going to have to dissipate a lot of power, 20 and a half volts at 2 amps, it's 41 watts, okay? So let's say at 2 volts, 41 watts that we have to dissipate. Now with the new circuit at 2 volts, oops, I guess you're not seeing that. Yeah, you are okay. So in without regulation, without using the selector to select the different coils from the transformer, and going directly from 22.5 volts 2 amps here through the regulator and to regulate down to 2 volts, without that, without selecting the coil in the transformer for this one, when we want to regulate down to 2 volts, we would have to dissipate 41 watts. So at 2 volts, we have 41 watts. Now with the new circuit, we have 4.8 volts here, because we are selecting only this inductor. So we are dissipating the difference from 4.8 to 2. It's 2.8 times 2, 5.6. At 2 volts, we are now at 5.6 watts. And let's say at 4.5 volts, yeah, 4.5 volts, we would have 22 minus 4.5, 18, 36 watts. 36 watts, and with the new circuit, so we were getting 8.2 8.2, 8.5, 8.5. 8.5 is what we are getting here when we select this coil. At 4.5 volts with the new circuit, actually using the selection instead of directly from the 22.5 volts, it's 4 volts. The difference is 4 volts, so we have 8 watts. Okay, let's do one more. 5 volts. So for 5 volts, earlier we were going to have 35 watts, and now we are going to have 5 volts, 22.5, 7 watts. No, sorry, no. How much are we getting there? Forgot. I think we were getting at 5 volts. Let me see how much. Better be sure. $11.5. So at 5 volts, we are going to get 11.5 minus 5. That gives us 5.5 times 2. It's 5.5, 11 watts at 5 volts. And now 6 volts is going to be 15. 6 volts here, 15. Well, 2 less watts, so 33 watts. 33 watts. And here from 15 to 6 we have 18 watts. Okay, as you can see, this thing is just going up, but while this one is going down, but 41 watts as 2 volts, it's quite a lot. Now let's do the other one. 18 volts at 9, 18 and a half. That's what we are getting. I'll just do the last one, at not the first one. Well, that would be interesting too, right? So I'll just at 9 volts. We were gonna get 6 watts less than that. 6, that's 27 watts. 27 watts. And let's do the 12 volt as well. 12 volts, it's gonna be 27 watts minus 6, 21 watts. This is for the old version. Now, for the version without selecting, without using these values are for using only the last coil, well, the 12 volts and the 0 volts, and going through the rectifier. And now with this coil selection, let's see, 9 volts. At 9 volts, we are going to get 18.6 from the coil. 18.6, that's 9.5 times 2, 19 watts. 19 watts. And at 12 volts, we are getting the 22.5 volts. Minus 12, 10.5 times 2, 21 watts. Okay, the last setting is going to be dissipating about the same, but mostly we are using way less power. So one other thing we could do here to improve this is that, for example, let's say we are at the 2 volt setting. Actually, there's the voltage drop on the regulator, which is roughly 2 volts. So the input voltage into the regulator should not be 2 volts lower than the output. So should be 2 volts higher than the output. So let's say at 3.3 volts, we need to have 5.3 volts, which would actually not, we would not get from this point. So we need to go to the next one, right? So that means that we should actually disconnect number 2 from here and short these two from number 4, right? So in the new circuit, we are going to short 4 to those 2 pins and disconnect 2, because we can get 8 volts. That means that this value is going to go up. It's going to go up, but we know that we have enough voltage in the input of the regulator to get 3.3 volts. Actually, for 5 volts, the same, because we have 8 volts, we have a difference of 3. We can probably do the same, although I'm not very sure if at 2 amps this is what we are getting. So that means that pin 4 would actually serve these voltages, 3.3, 4.5, and 6 and 5. So for 6 volts, it's probably taking it too far. We still have to get 6, so that we will keep it like that. For 9 volts as well, so for 9 volts, we can actually lower the power dissipation here. Instead of 19 watts, we can get less than 18 by using number 6. So this would be number 6, and it would be shorted there. But we have 11.5 volts. Actually, number 4. We have 8.1 volts in the input. Oh, what is this? Yeah, just a matter of drawing it properly. So 8.1 volts, 11.5, and this would be this will be third, 1, 2, 3. This would be 6, yeah, and this would be 4 on the transformer, right? For 13.8, 11.5 is not enough, so we need to go to the next one, which is 10, not 12. So actually 10, 8. So here we are going to connect 8. So those two, we are just burning power by connecting to 10 or 12, because on number 8 we have 15.1 volts. So we will lower all these values. For example, let's see here, 15.1 volts to 13.8. Let me calculate that. So 15.1 minus 13.8, it's 1.3. 1.3. Okay, this is not enough. Can't use that. Have to go to the next one. Have to 18.6. It has to be number 9. And 18.6. Yeah. 18.6 volts. So let's say 18.6 minus 13.8 equals oops, 4.8. So 4.8 volts, 2 amps. This value is going to be 8.6 watts. For example, from 9 to 11 and a half, we have 2.5 volts, so we have 5 watts. Okay. Number 6, we have 11.5 volts. Yeah, that's going to be a bit higher. Not here. It's not going to be higher. It's still 6. This one is still the same, 18 watts. And 5 volts. 8.1 minus 5 is 3.2. We are going to have 6.4 watts. At 4.5, we're going to have one more watt here, so 7.4. This one was wrong because actually we could not have 3.3. Let me see something. 4.6 volts to 3.3. 4.6 to 3.3 is less than 2 volts, so we need 5.6 volts at 5.3 volts at least. So this doesn't work. Okay, so we can't have that because at 2 amps, actually not even resting, the 4.6 volts of input from number 2, that would give us about 4.6 volts here, is not going to be enough to get an output of 3.3. It would be enough to get 2 volts, so 4.6, to get 2 volts here we need another 2 volts, so that would be 2.6 volts across the regulator, which is okay. It's probably not a good idea to keep it so close because as we load this with 2 amps, the voltage will drop a bit. So now this time we have 8.1 minus 3.3, it's going to be 4.8, 9.8, 9.6, 9.6 watts. We had another one that was, yeah, this one was also 4.8. Yeah, this is also 9.6 watts, 9.6 watts. But no, as you can see now, we are only dissipating more than 10 watts at 6 volts. And it's 18 watts, which is going to be half of what it would dissipate, not half, but yeah, almost half of what it would dissipate in the 6 volt setting there. So by doing all these changes, rewiring the inductors, the secondaries, and getting this much more, and getting this regulated, but changing the voltage here as we need, as we change the desired regulating output, we will be dissipating way less power, and this is going to still be a linear power supply, which is quite an important thing to use in a radio equipment or even audio, because a switch mode power supply outputs a lot of noise and EMI. So maybe if you trying to make your audio circuit sound great and not get a lot of noise, you can use something like this, but still have kind of an advantage of not dissipating as much power as in the typical linear power supply, which would use only one one secondary, and it would regulate down from that high voltage and dissipate a lot when you are using low voltages. So that's it for today. If you want to do the thing, just do a print screen. On the next video, I'll show you how to assemble this thing and make it kind of usable. I'm not sure if I can get that switch to get the terminal in that switch, or if the terminal is still there. I'm going to open it, and if not, I have to replace the rotary switch to get terminal B, which I couldn't see. So that's it for next video. Have a good one.